All right, thank you very much for coming. The subject matter that we're going to talk about is how to do the same thing that we do in Rust for runtime polymorphism and capture that in C++, which will give us a lot of advantages and options that we can profit from. So, who are we? What will we do? Myself, I am the lead of the open source library called SU, as in the namespace SU. We have done published things that have been communicated to the community in several presentations by my collaborators and I, including SWART, type erasure, a hash table based on the Robin Hood invariant and other things. Before, I was a team lead or a tech lead at companies such as Snap and hedge funds that do automated or high-frequency trading. So there was an environment that was very challenging because, for example, in Snap, object code size matters a lot in the mobile space. At automated trading, low latencies are paramount. And the things that I try to communicate with the community are things that are amazing that can only be done in C++ because of the specific characteristics of the envelope of abilities that C++ gives us. And just to let you know, I am Rust skeptic, but I hope that we all can learn from good ideas from other languages. And I want, by show of hand, please tell me who among the audience is a fluent Rust programmer? Okay, I see about a third of the audience. So that's very promising because that is more or less the target that I was aiming for. So we're going to go about showing you a little bit of Rust code so that you get familiar with it and get the flair for it. But it's going to be very C++ centric. And also, we're going to be going over things that are more or less on the theoretical nature, because in my opinion, we're going to be straddling such a cultural gap between Rust and C++ where we better know in depth the concepts that we're going to be talking about. And I hope that that's going to be helpful to you because in one-to-one trial runs of some bits of this presentation with friends that I used to get feedback, they have told me positive feedback about a little bit refreshing way to explain things that we have been studying for a long time. Okay, I'm gonna make the abbreviation in the slides of RP for runtime polymorphism. It is a mouthful, and sometimes I will not say it. There is a series of presentations in which I have covered this topic, and there are other, for example, the presentation by Fedor Picos at C++ Now last year of type erasure demystified, which I'm going to include it in the series because they mutually reinforce. There is some overlap between them, and they mutually reinforce. Okay, what we're going to be doing today is something that is nearly impossible. Instead of the feature for runtime polymorphism in the language, which is virtual inheritance, we're going to use user code, in particular a type erasure framework, that allows us to synthesize benefits from the Rust programming language feature to do runtime polymorphism, which is Rust rates, while still in C++. And if we survive the challenge of understanding all the necessary things really well, which is truly important, the part of really well, then we're going to get a best of all worlds combination. And that implies better performance, better object code size, and more modeling power too. And meaning that we can represent what we want to represent with greater ease than what any of the individual languages will allow us to. So how is this possible? Well, it's because of C++, of course. It has the characteristic of performance preserving or increasing even abstraction, because when you use the mechanism of C++, you inform the compiler of many more things than other languages, and therefore it can optimize further than in other languages. C++ has this attribute of not committing to any particular one true way of doing things. It is skeptical of itself, so it lets users do things that might rival the internal mechanisms in the language at times. It is also because of our community's resistance or tolerance for outstanding complexity, so that doesn't scare us too much. And I'm telling you this because I really hope that this presentation shows you the value of coming to these conferences, how we gather each other, how we gather so that we can help each other. Okay. We have to arrive to nearly the proficiency of language designers. Let's start that journey. Before our focus is, what we are not going to talk about is the compile time powers of raw traits, things like concepts like monomorphization and those things. We're going to not talk about the runtime polymorphism in the style of Rusty nums that resemble standard variant. We're not going to be doing comprehensive coverage of all the features and options, nor we're going to be talking about Rust to C++ bindings. Was anybody expecting that we were going to be talking about Rust and C++ bindings? I see that nobody raises the hand. That's quite a relief, because I didn't put that in the abstract, and I regret not having to. Yeah, so the real focus is on guidance, on how you guys are empowered to do what I'm going to be showing you by example. So what I'm going to show you is just an example. The idea is that you can do it on your own with some other type erasure framework if you want. My type erasure framework, that doesn't matter. What is the style of runtime polymorphism of raw traits? Alas, I cannot tell you the style part, but let's start with what is runtime polymorphism and why it is good. I know that everybody knows runtime polymorphism and why it is good, but let's review that. The issue is quite simple, in my opinion. We need to identify the essentials to not have to deal with irrelevant details. So it is an exercise of focus. And what do we do when we capture the essentials of something? Among other things, that we understand it much better, and therefore that helps us tremendously at every single step of the way. But if we use some pseudo-mathematical reasoning, there is also an idea of reusability that is very true, and I want to flesh out in more detail. Which is, if you have n implementations of a mechanism that your code base wants to use in m different ways, then in principle, you're going to have a combinatorial quantity of combinations of the implementations and the uses. So you're going to have the multiplication of those two dimensions in the pieces of code. Now, if you do the work to come in with a good abstraction, let's call it an interface, then perhaps you're going to have the same n implementations and the same m uses, but the total amount of pieces of code that you're going to be doing is 1 plus n plus m. And of course, if we get it right, that's going to be a huge win, right? So it's really important that we have all of the tools necessary for us to come up with great abstractions that relieves us of work as opposed to introducing work for us. And what we're going to be doing, again, is abstraction. That process of identifying the essentials is very much what we can talk to as abstraction. And also, if we get good abstractions, we get conceptual leverage. Now, runtime is simply that the actual implementation is not known when compiling the code. So that you're going to see later that the code during its execution discovers what are the implementations that it wants to use. Therefore, they are not known when you were compiling the code. Polymorphism, well, hear me out because this is subtle, and I hope that at least some of you see this for the first time. The whole idea is that no matter what the implementation is, that you can substitute any implementation in the code, and things will just work. So that multiplicity is the part of poly, and the morphism is the behavior. So that is the Liskov substitution principle, which was named after the inventor of the concept from UCLA, Barbara Liskov. And I say UCLA because I live in Los Angeles. Were you all already aware of the Liskov substitution principle and Barbara Liskov? Please raise the hand. Okay, I see about 3/4 of the audience. Okay, in the style of traits, I cannot tell you what style means at this point in time. It's better if I do it later. So let's start with part one. The introduction is over. We're going to have the concept of a type, which is what we normally refer to as an interface, and the subtypes are going to be the implementations. Warning, most languages, including C++, conflate both things, subtyping relations with subclassing relations. And we will see that that is precisely the bulk of the problem they're going to be solving. And that's what we are not going to be doing. And let us introduce everything by a simple example that hopefully is going to be familiar to all of us, which is the example of serialization. So let's say that we have this interface of serialization. Are you able to see read the slides from the back? I see that there's not a problem. Okay. So I hope that this is not unfamiliar code for any of you, right? And what we want to serialize is an integer. But integer does not inherit from the interface of serialization. So we had to start doing busy work, which is wrap our integers into a wrapper type that inherits from the serialization interface. We're cool. We will write the integer wrapper as a template, so solve the same issue of wrapping for everybody. Well, we are at it, and we come up with something like this. Don't focus too much on the details of the code, because I assure you that when you see later the slides or the presentation online, it's pretty much what you will expect. It is a template that takes an arbitrary type. It is called a serialized wrapper because that's what it does. And it fleshes out two routines, which are the APIs defined in the interface. Now, what are the problems with serialization as subclassing? We just stumbled with one major issue, which is if your subtyping relation is invented or discovered as needed after you have written very good types, then you're in a bind, because either you re-express, redo, rework, retrofit the inheritance relation to the existing types, or you had to come up with wrappers for them. And these can get very quickly very nasty, because let's say that you want the same types to participate in other subtyping relations and participating in all of them simultaneously. Then you had to have wrappers for each of the individual interfaces, meaning that one wrapper needs to implement all of the interfaces. So every time that you use another subtyping relation, you had to retrofit that subtyping relation to all of the wrappers that you had before. Well, I really like that Rust traits don't have these problems. The tragedy is that subtyping has subclassing is the most popular and the worst way for doing subtyping, okay? So this is something that our colleagues that designed Rust, they knew better than falling into that pitfall, and they gave us something that we're talking about today. All right, how does that look in Rust? And I'm really happy that 2/3 of the audience, more or less, told me that they are not very fluent Rust programmers, because perhaps some people might see these things for the first time. Okay, I declare a trait that I call it serialize, and I put in there one API that does the work of taking the self. This is the equivalent of the this parameter, but has a non-mutable reference. And because it's gonna mutate the thing that it's gonna write to, it takes a mutable reference, and then it produces a monad of result return value. So after you had declared that, the slide shows how to give something that is primitive, that predates the trait, how to give the capability of serialization to something like an integer, or any type for that matter. And what you do is to say the implementation of serialization for an integer is to do what the code shows. And if we want to see more robust example, this is compilable Rust, I believe. And we are defining a user type called point. And we are making it so that it's going to print it within parentheses and a comma. And we keep the serialize for integers that we showed a moment ago. So what are Rust traits? An opt-in mechanism for types to participate in subtyping relations. This is not related to inheritance, which is a structural property in C++. It does not need base classes. It does not need the wrappers. So those things are absent from the universe of problems that we have. So Rust traits have a lot of interesting things for compilation time, because unlike, for example, in C++, that if you invoke a function that has overrides, so that is virtual, even if you wanted, no, I really want to execute the function defined in this type, the dynamic dispatch is going to be activated. It's kind of tricky to get that. So you can do that in Rust at compilation time, which is good. But that's out of focus of what we're doing, because in C++ we have such phenomenally powerful things for compilation time that we don't have to embarrass Rust by making the comparison, okay? So another thing is that it truly captures the essence of the benefit of Python's doc typing, which makes Python, one of the reasons that Python is very popular, in my opinion. It's just that you have to be explicit in the binding between the objects and the interfaces, all right? So that's quite an acceptable trait that I'm happy to endorse. Now, let's see something that is a world of hurt in C++, that we try to use has a member variable, not a reference, a pointer via smart or dumb pointer, something that we want it to be, to have the capability of runtime polymorphism, but at the same time be a member variable. The problem is, of course, slicing. And let's say an interface, a runtime polymorphic interface, typically is empty of all data. So its size is just the virtual table pointer. But any implementation will almost for sure will add data members into it, right? So if you assign something that is bigger to something that is just an interface, an instance of an interface, sure, you're gonna fill properly the part of the interface, but you're gonna damage all of the siblings that are right after the member in your data layout for the user type. And to make things worse, your code can pass unit tests, can work in production apparently, but as soon as those corrupted sibling data members are needed, then you get a catastrophic error, and that's a Heisenberg. And the compiler lets you do this because, well, again, in C++, we can do whatever we want, so we better know what we're doing. And another problem is the inheritance, the intrusive nature of inheritance. Number one, it forces a structural property just for the sake of infusing something with runtime polymorphism. And I think that is not an acceptable thing to do, because the structural property of inheritance is to describe a relation of is A, not can do what this interface requires. So we are like using the wrong way to express things for the purposes of infusing runtime polymorphism. Of course, this was designed, 45 years ago or thereabouts? Because it's not when it was released to the public, but when it was designed and thought about. Well, okay. Another problem that I just showed you concerning the slicing is that this forces referential semantics. So not just that you have an indirection that requires an allocation and a lifetime management explicitly and so on, right? But that you're working with a reference, and that incentivizes sharing the state, disables local reasoning, and a host of other problems. So when I was writing the slides, there was a numbered list overflow, and now there is a software overflow, which is, I should stop talking about this because I have monopolized the time of other presentations on just this topic. Okay, so the subclassing pains are that we need to wrap perfectly good types to put them in a hierarchy, and that's busy work. And the typical example is wrapping integers in something like a serialization interface. And you already explained the problem of retrofitting and the problem of avalanching when you want your types to participate on several subtyping relations simultaneously. So it's much better that both of them are a separation of concerns principle away from each other. Another problem that I see with inheritance and virtual is that the specific way in which it is designed into the language, I find fault, defects on that thing, but it is a take it or leave it feature. Something that you cannot argue with, you cannot modulate in any way. So like, for example, there are several teams that altogether disable the generation of any runtime type information because the rules of the language make it so that every time that there is a virtual, there has got to be a thunk of RTTI that is completely useless and worthless, but it has to be generated because it is part of the design of the language. So there's no way to tell the language, okay, I want virtual, but please don't bother with the RTTI part because I'm not going to use it, for example. Okay. And there are many more problems. And I haven't watched this presentation because it happens that when we were at C++ on C, Nikolai Yosutis and myself were at the same time slot, but I'm really confident that Nikolai Yosutis did something great. And the YouTube video premieres in 14 days. And so we can make a party to watch it together. Okay, so how do you use a trait in Rust? In general, you just make it a member, right? And you have to use some magical incantations, like the Dean part, and outside of the Dean, the box part, right? And these are technicalities of Rust. The issue of the Dean is necessary because the serialization is going to be used in dynamic dispatch, and the compiler, when it is compiling this, it doesn't know what is the size of the actual type of object that is going to be the thing under the trait of serialize. And the part of box is so that you tell in your specification exactly how you want to keep it. And this is basically a so-called fat pointer, in which internally it has the pointer to the value and the pointer to the virtual table that implements the runtime polymorphic APIs. And there are other ways to hold the value, like you can have an RC, reference counted, and so on. The thing is that I didn't put it in the slide, that's on mission. The box actually has value semantics. It has an indirection, but because it is exclusive ownership and so on, that is the indirection from the point of view of semantics is transparent to you. Therefore, it is value semantics. So you have the really bad part of needing an allocation and having an extra indirection that makes everything pointer chasing and slower, but at least you didn't lose value semantics. In the solution that we're going to see in C++, we're going to see that you can get value semantics most of the time if you want universal, or absolutely all of the time if you disable altogether the possibility of having to use the heap. So it's your choice. And this is just a declaration of the user type. And now this is the implementation of the user type. And then we're going to see more details of Rust. Like, for example, in the part of T serialize plus static, like this part here, serialize plus static, it isn't Rust is culturally different to C++, and you have to be careful of not looking at things having references to objects that don't belong to you. And static is a way to say, yeah, this is not going to have views, references into things that are outside. And don't get scared too much about it, because once you begin to program in Rust, it flows. Or this is not something that becomes a hindrance. And the way to use it will be, well, very trivial, right? Like if you want to mutate a buffer, and you want to mutate a user type, and that's the way that you invoke serialization. You rebind the trait to some other object, and again, use the runtime polymorphic that it offers. Now, in the style of part of the title of the presentation, there is a big gap ideological between Rust and C++. So the things don't translate one-to-one. Rust is very serious about mutability, and it gates the problems of mutability by requiring you to do something called borrowing a reference, and then there is a borrow checker that guarantees this property. There can be one mutable reference, or as many as you want non-mutable references. You cannot combine the two. And the thing that enforces that is the borrow checker. In C++, of course, we do whatever the hell we want. So it's like a very different. And of course, that Rust has to allow the programmers to do things that the normal invariants and conditions that are guaranteed by the compiler and maybe even the runtime. And for that, there is unsafe, right? Which is basically, trust me, I know what I'm doing, type of code, and should only be used when necessary as opposed to liberally. Another thing is that in Rust, moves are the default and implicit, and the copies are opt-in. And the reason being that really helps with Rust's error prevention. There's no implicit copy on pass or assign for owning types. There is a very clear split between copying that they make it mean just a trivial copy like the bitwise copy of the values versus cloning that copies substructure and might have to do some work of allocating a new resource like new memory buffer or opening a file or whatever, right? That and the borrowing rules make it so that the compiler prevents use after move and aliasing bugs by construction. So they cannot happen unless you of course, destroy the guarantee by using unsafe in the wrong way. So Rust, in a sense, has a lot of restrictions so that you carefully work around them, and that saves people from the typical foot guns on C++. You know, we don't have feet anymore. We are all cyborgs because our feet have gotten so many shots that we had to replace them with something cybernetic, right? So, bugs by construction. There is one major limitation that we have that I cannot help, or I don't know how to help. I haven't seen a way to express the rules and the borrow checker so that we can benefit from Rust error prevention. This is a feature of the language, and synthesizing the feature of the language in C++ via the user code is doable, but it requires a very serious amount of work to make something that is practical to use. Also, we can learn from the style of Rust and constrain ourselves, adopt that as a discipline. By the way, the struct user type that I showed you is move only. Now that I have explained that moves are by default and implicit, and the copyability is an opt-in that takes real work to do, and I can tell you that that structure is move only. Okay, so now what's going to be the solution? How are we going to adopt those benefits of non-intrusive runtime polymorphism into C++? Well, we're going to use the technique of type erasure. And the precursor to type erasure is that there is a design pattern called external polymorphism that allows you to, from the outside of the type, give runtime polymorphic capabilities to a pre-existing type. Now, if we also do external polymorphism of the ownership routines, destruction, moving, and potentially copying if you want them, then we have absolute control of the object. We can do whatever we want with it, right? Because we have absolute control, then that's what we call type erasure. And I went and made a presentation now out of the apparent contradiction between type erasure, which I call it internal external polymorphism. That's at C++ Online and C++ Now of this year. So the best description of external polymorphism I ever seen is in the book C++ Software Design by Klaus Eagleberger, who is a frequent presenter at CppCon itself. This is the cover of the book, and I wholeheartedly recommend this book. The part of external polymorphism is really well explained. The part of type erasure is the best explanation of type erasure, but there is a conflict of interest because he mentions my work in that chapter, so take it as you want. Expression of traits in C++. to synthesize runtime polymorphism in a different way, we will use, in general, the gist of what we're going to be doing is to use the excellent compile time polymorphism capabilities of C++ to synthesize runtime polymorphism capabilities. And the way to do that is to basically imitate, or one way among the many, but this is truly practical, is to imitate the way in which the compiler creates the virtual table and does all those things. When I say virtual table, do I leave everybody on board? Or yes, okay. The people didn't even bother to say yes, but it was very clear that it was unanimous. Okay, how to build a virtual table is something that we absolutely need. After that, we need to devise either fat pointers or the type erase containers, or they are the same thing, that manage a value and link them to their virtual table. Why do they need to link the values that they manage to the virtual table? For the obvious reason that they have to perform the virtual dispatch or the dynamic dispatch. Sorry, I said virtual dispatch. I should have said just dynamic dispatch. A mechanism for the users to be able to extend type erasure containers with the equivalent of their ROS traits. Okay, so there exists a type erasure framework. How would a user use their trait in that framework? Let's say that the user wrote a serialized affordance. Serialized affordance. That's the user trait. And okay, how would the framework allow the incorporation of that capability or affordance into runtime polymorphism? All right. So let us read from the bottom up. The suDestroy, suMove, and suCopy are just the basic affordances, the basic capabilities, the ones that flesh out type erasure. Among other things, if you don't use suCopy, for example, then it would not be copyable. It would be move only. If you want it to be copyable, then you put suCopy in. If you want a different destroy mechanism, for example, a destroy that does nothing, because those objects will be taken care of by program finalization anyway, so why put all of the binary object code of the destructors of things that you don't care about destroying because the operating system is going to take care of wiping everything out. You can make the selection of a destruction affordance that does nothing, and so on. Then the void pointer there, that is the specification of the local space. It's not that you're going to have a void pointer. It is that you're going to have something aligned and of the size of a void pointer to work locally to put values there, or perhaps a pointer to the heap. Okay. And those things are given to the policy builder in the framework. And you can make the mental substitution of configuration for policy. And in this line that we're defining the container, we're just indicating the policy has the argument to any container. So any container, as the name suggests, is an extension from standard any. Not an extension from standard any, sorry. It's inspired by standard any and to a significant degree. The way to use the serialized trait is you pass it, has a const reference, a value, or whatever you want, and invoke the member ser into that container. And somehow that's going to activate the runtime polymorphic API. And if you want to make one, you can construct it, or you can write a make function that in this particular case is just going to make a serializable out of an integer. So I hope that this is relatively understandable. Any questions? Okay. Now this is the entirety of the code of an affordance. This wall of code is actually less frightening when you inspect it in detail, and that's what we're going to do momentarily. But that's it. Like this is the serializable trait expressed to be used with the SU type erasure. Now, once we have done the trait, we can see the part of the dynamic dispatch and the virtual table mechanism, right? In particular, an object of a type that is serializable, something that can go inside a serializable, will have a virtual table with pointers to the implementations of the functions for serialize and length according to what we defined at the beginning of the serialization interface. That's not the only thing needed because we need to have full control of the thing. So we need destruction and movability and optionally copyability too. All of these runtime polymorphic behaviors will be activated by invoking the function pointers in the virtual table. Then the objects must have all of their state and a pointer to the virtual table. That's why they are fat pointers, because you had to refer to the object in some way and at the same time bind it, associate it to the virtual table point. And by the way, that's the same thing that happens with virtual and overrides, that implicitly your memory layout of your polymorphic types begin with the pointer to the virtual table, right? And of course, this is taken off by the type erasure framework. So how is it taken care of? We're going to see this live later, but let's first. So within serialized affordance, which is the wall of text that I glossed over a moment ago, there is a substructure, a subtype that is called, it needs to be called the vtable entry because it is picked by the name vtable entry in a way that I'm going to show next slide. And what it says is, for any runtime polymorphic object that has the capability of me, then please put two function pointers with these signatures in the virtual table. So good? Questions? Okay. So the way in which the framework does, remember that we were giving this to the policy builder. The policy is an alias for this structure. And this structure takes the holding model, how you want to model the local space, and a variadic pack or a pack of affordances. And so the vtable is the composition via inheritance of the vtable entries of each of the affordances. And it has some ergonomics, like the ability to do an upcast, and in some other place there is a template that from the total, the global, not the global, sorry, the complete virtual table for the container to refer to the part of each individual affordance by using the affordance as a template argument. And this line, by the way, is of course the same thing, has overload to be used in variant, but the lifting of that idea to a scenario in which you are doing a composition via template parameters, I think that this is probably the most successful line in my career. And by the way, we have done 70 slides already. I hope that you are enjoying yourselves and that some of value has already happened. I show the number because, of course, if you later have a question, take notice of the slide number, and we will refer back to it because we are stepping up on complexity, okay? Now, how to implement the virtual table. The framework is going to tell the functions, the framework is going to tell the affordance, the concrete value manager, that is going to be managing the object that is going to be doing the work. By the way, one of the reasons why it is the concrete value manager as opposed to a void pointer to the object that is being managed is because a concrete value manager might not offer the value. It can do things like scattering, data-oriented scattering. And so the fields are going to be scattered into arrays of structures, in an array of a structure of arrays of fields. So the framework by itself does not commit to to maintain the object somewhere. It can give you proxies to the fields that it has. Okay. But in this particular case, this affordance is prepared to use the concrete value managers that have the function of value. And now it is a good time to inspect the signature of the function pointers that are being initialized with non-capturing lambdas here. And you're going to see the use of const void pointer or void pointer. That's because a void pointer is a universal pointer. And the concrete value manager is the one that is going to tell the affordance what is the concrete type, hence the name of what it is managing. And so the code obtains the pointer to the value and uses it. That's what the slide means without having to read it in greater detail. So now we have runtime polymorphism. We're getting really far ahead. So how is the dynamic dispatch mechanism bound to the user observable capabilities? The affordance, the user affordance, the trait equivalent needs to provide the user affordance member that is templated on the complete container. In this particular scenario, if we go back a few slides, would be the any container on that policy. And it's going to use the curiously recurrent template pattern downcasting, it is. Yes, it is downcasting from, because user affordance becomes a base class of the whole container. You can downcast to that container, and that container, unfortunately, I chose the name of container to refer to the value manager, but that's what container means. And so value manager, and the value manager allows you to have access to the virtual table. That will be here. Allows you to have access to the virtual table, and you can access the serialized implementation. And that's how you get the pointer that you want to call, and that is the invocation that ties all of the facilities that we architected to be made available to the user. Okay, so let's recapitulate. In particular, I want you to observe that this identifier is what we use on serializable, which is an any container. Serializable is an any container, and it has the member function set. We can go to the compiler explorer. Questions? Oh, all good. And they are not asleep, by the way, so things are going well. Back in planet Earth, I have shown you that we do the same things that Ross traits do. We have subtyping without subclassing. The nature of this runtime polymorphism is opt-in. We are also using overloads and templates to implement the trait for all types that satisfy a property. For example, being insertable to a stream. That's what was taken care of in the implementation function Like there is an implicit catch-all that is the function how to serialize that takes the pointer to the value. No, sorry, no, doesn't take the pointer to the value. Takes the reference to the value, and this reference to the value, of course, it has the full type of whatever is contained in the any container. And Rust allows you to accomplish what I showed you a moment ago in C++. Has a so-called blanket implementation for all types that implement the trait. So this will be the way to do it. So the impl t column display is restricting what we will call the template parameter t via the concept of display. By the way, formally, Rust traits are similar to C++ concepts. It's just like I said that we were not going to talk too much about the compile time capabilities of that language feature. So we can recap. We can capture runtime polymorphism, the style of Rust traits. We have succeeded at making it opt-in subtyping without inheritance or subclassing. We have completed sidestepped all of the problems, but we have advantages. You saw, for example, that in my framework, it is absolutely transparent to the user. They have value semantics through and through, and because the user can configure the buffer to what they think is best, they can perhaps choose to use a configuration for the local buffer that is very, very large. So you would almost never have to punt to the allocation on the heap. Or you can make it so tight that the only space available is for a pointer, so everything is going to go on the heap, and therefore box and such an any container will be basically identical. Another choice that you have is to not use the big policy constructor, which is a SU policy, but put the bits together in your own way. I can show you an example of that if you want, so that you altogether disable heap allocation, for example, so that you are, from that point on, it will be a compilation error to try to put something that won't fit in the local buffer, or vice versa, or maybe even do something really cool, which you cannot do in Rust, which is that your value manager is not on the heap, has a reference by a normal pointer or local, but that there's a third option of it being a shared pointer. And then you can share the actual object via some other shared pointers and so on. I have shown this in other presentations, so I'm just mentioning that all these possibilities are available. And I want you to really think about something that I believe is the most important part of it all, okay? That we are synthesizing programming language features in user code. That's why we have so much power, so much in terms of capabilities and modeling power and even performance. And why performance? Because we can make the optimal choices for our needs. The choices that cannot be offered to us by take it or leave it programming language feature. And then you have the wonderful characteristic that will remain within C++. And the conclusion is that C++ is that powerful. Thank you very much. I am ready for questions. And while people develop the courage to ask me a question, I'm going to go back to the links on the Compiler Explorer and get them ready, because we have time to see some of that. I had to unplug for a moment because I don't want to.
You don't want to hear your room numbers?
If somebody wants to tell me their room number and last name, I can use it. Sorry about that. This is going to be disrupting. I am past the annoying advertisements. Okay. Do you guys pick up the computer again? All good? Yes. So maybe Tronca is not working at the moment, and we can use one of my preferred ones. Clan 20 is going to be good. Yeah. So this compiles. So when you get the slide deck, you're going to see a link, and the link compiles just fine, and you're going to see the assembler and so on, right? And like I think that I lost track of what was the page number of where I teased a compiler expression. Oh, questions?
Like, do you have like where it's put together? I guess that's
Yes, that's a very good.
It's like, what are you doing with all of this?
So thank you for that. So it's very easy. So GitHub the CPP zoo, and you're gonna get to the zoo library. And my recommendation would be to always start with the test directory, okay? Because the test directory is out of line from the headers, and it has unit tests in catch 2 that illustrate how to use the things, okay? And look, just gonna show you. This is another affordance, but well, you can see affordances in here. So this is a user affordance. You can also see the infrastructure code affordances. And again, it has a debit table entry. The default, this is for default constructed containers. Basically, what you're gonna do if you are involved with something that doesn't have a value in it, are you gonna creak with throw an exception, for example? Oh, by the way, another thing that we have has an advantage of doing this in C++ as opposed to in Rust is that we don't have to abide by the monad of result. We can use exceptions. Again, this is an operation, something that is for advanced use. The user are funded, so you can see here that in principle, string guys is going to be something that. So I am running out of time. The two tidbits that I wanted to tell you before we end is that both ChatGPT and Claude in particular, which are the ones that I have run the tests, if you pass it you pass it this, what you see in the, no, sorry, not this, the compiler explorer code that is self-contained, if you paste it into the LLMs and ask questions, miraculously, they are going to give you almost certainly correct answers. And I'm really interested in it's another recommendation is, if you want to use these, contact me, okay? Because this code is ugly and incomplete for a reason. And the way to get. So thank you very much for the attention, guys. I hope that it was of your benefit.